So this short video will cover the dielectric materials and boundary conditions in electrostatics. And in the schematics we see the main idea behind the main behavior of dielectrics, which is to internally distort the charge distributions according to the applied field. So also here on the left we have an atom in an external field 0, which is symmetric, and the negative charge is uniformly distributed around the positive nucleus. And once an external applied field is imposed on the material, this charge will rearrange itself because of the electric forces that the charges experience. But because they are bound to each other, they do not have enough energy to break free, and they stay in this charge configuration in dielectrics. And what that does now is that this atom itself is setting up a small field from its positive charge to its net negative charge center. So here on the right we see this effect here in larger schematics of a dielectric with the polarized molecules due to the applied field. And we can see that the total field now is going to be something a little less than the applied field, and given by the sum of the applied field plus the internal field. And because of that, because the internal field is in opposite direction to the applied field, the magnitude of the total field is always greater or equal to the applied field. And this amount of internal field, the response depends on the material. So some materials are able to polarize more and to induce a stronger field. There are more charges to induce this internal field, and most materials respond linearly to an applied field within moderate magnitudes of field. And that linear relation is expressed through this polarization field E that has the same units as displacement vector field E, and it's called polarization field or electric flux density that is induced by electric field E. So if we have our material with some distorted charges in response to an applied field, these charges are setting up an additional internal field in the opposite direction, and that can also be expressed by this material polarization field that is along the applied and the total electric field, and the magnitude of which depends on the electrical susceptibility, which is related to the dielectric permittivity of the medium. So as we can see from here, we can express the total field E as the field that would exist, that would be applied if there were no material there, if it was vacuum, divided by the total epsilon, which is the epsilon naught times the relative permittivity. So the higher the material relative permittivity is, the lower the total net field is. And for if the voltages reach sufficiently high values, the material eventually breaks, and that is called that maximum voltage that you can apply across a given dielectric is it's called dielectric strength. Before it breaks down, before those charges become loose and can contribute to conduction rather than polarization within the material. And here we have examples of this dielectric strength for some common materials, from air, which differs from vacuum just by a tiny bit, but it's sufficient to have a different breakdown field. So you can see here the breakdown fields are on the order of 1 to 100 megavolt per meter. And the higher, the general trend is that the higher permittivity, the higher the breakdown field is. Now we look at the boundary conditions in electrostatics. That are derived from Maxwell's equations for electrostatics. The divergence of the electric field is the volume total charge density divided by epsilon naught, and this can also be written as the divergence of the displacement field D is equal to the volume free charge density in the region. And if we apply Gauss's theorem to, we know that this is equivalent to say that the flux of E or D is given by the total charge enclosed by this surface. And if we choose to a box that is symmetrically placed around this interface between two different media, we can see that as we make this box become thinner and thinner, the flux will only be given by the normal component, which has flux through the top and bottom cylinders, and that gives us this normal relation for the boundary conditions for the electric field. So it tells us that the field, the normal component of electric field, might be discontinuous, because this is what the flux will give us, if there is any charge at this interface. If there is a surface charge density here, then the normal component of the electric field will be discontinuous by that amount. And similarly for the tangential components, we are using the curl, the second Maxwell's equation in electrostatics, that tells the curl of the electric field E is always zero, and this is equivalent to say that the circulation of the electric field is always zero. So in order to relate the tangential components of the field on either side of the interface, we can choose this path, a closed path C, with long side on either side, and again make the height or the width of this path go to zero, so the circulation is only given by this left and right segments of the integral. And because it's always zero, it means that this integral has to be always the same, so, and the length is the same, so that tells us that the tangential component of electric field is always continuous. And from there we can relate the displacement field D in on medium 1 and medium 2 by their relative permittivity constants.